Assume that you're a medical doctor creating a new drug. You look at one specific blood level, whose average in the population is, to keep things simple, say 6.00. And then you treat, say, 100 persons with the drug and look at the results. Of course, you would do that with a spreadsheet. So here's the 100 data points that I invented. Let's compute the mean of the cells A1 through A100 and the standard deviation of the same cells. So we've got a mean of 5.81 and we've got a standard deviation of 1.05. This looks as though this level went down, but on the other hand there is a huge deal of fluctuation. Each single value goes up and down by approximately 1. So the question is, how reliable is it to say that the value has come down? There's one thing to note up front. This is the standard deviation of the sample of 100 persons. For that large a sample, we can say, okay, this standard deviation of the sample is pretty close to the actual standard deviation that we would get with millions and billions of tests. The way to proceed in statistics is to form a hypothesis and try to reject that hypothesis. So let's form a hypothesis, namely the hypothesis that mu, the expected value of this blood level, still is 6.00 even after the treatment. Expected value means the average of millions and billions of experiments. The next step in statistics is to compute one number of the data that we've got. Let's call it a statistic, a number that you compute from your experiments. In this case, the typical thing is the z-statistic. What we're doing is the z-test. So we take the mean that we've got minus the expected value that we hypothesize and divide by the standard deviation divided by the square root of the number of experiments. I'll explain that in a second. First, let's compute what this amounts to. So that's the z-score, and this is the mean minus 6 divided by the standard deviation. And now we have to divide the standard deviation by the square root of 100. It means the total fraction is multiplied by 10. That's our result. So the z-score is minus 1.82. This is minus 1.82. And the basic trick in statistics now is to check what the probability is of this value occurring given this hypothesis. We try to show that this value is highly improbable and hence this hypothesis cannot hold. That's what we're trying to show. Let's see what happens. I still have to explain why I form this strange looking fraction. So let's look at the distributions of these random variables. If, that's important, if this hypothesis is true, let's start with the mean of the 100 measurements. That's pretty much centered around 6. So this is what it's going to look like. Actually, the curve is way taller than that, but That's hard to draw in this diagram. If I subtract 6.00, and given this hypothesis, that's actually the center of this peak, if I subtract 6.00, I get a curve that's peaked around 0. So this is what x bar, the mean, minus 6.00 looks like. The central limit theorem tells us that this curve is bell-shaped and gets more and more bell-shaped as it gets taller and more narrow. To undo this effect of it getting taller and more narrow, I introduce this denominator. Again, this stems from the central limit theorem. This width decreases with the square root of the number of measurements, and the denominator undoes this effect. So z, the result, has always the same bell shape, independent of the number of experiments. Z has a normal distribution with mean 0 and standard deviation 1. That's our prediction, if this hypothesis holds true. And now I'm able to say how improbable or probable this value is. So if this hypothesis is true, and I test 100 persons, I may end up, for instance, with a z-value of minus 0.5, and then with a z-value of 0.9, and then with a z-value of 0.3, and so on and so on. Maybe sometimes 0.5 or minus 1.7, maybe even 2.1, but mostly in this region. This is what the bell-shaped curve tells us. Now we can use the normal distribution to learn what the probability of this value is. Actually, it's not the probability of precisely this value, minus 1.82, because that probability would be 0. We have to say it's this value or worse to get something that's different from 0. If we can show that this probability is small, given the hypothesis, then we know something's wrong about the hypothesis. So let's compute this probability using the normal distribution. Which is the standard bell-shaped curve. Our minus 1.82 is somewhere here. And we're looking for values that are even worse, so even more distant from 0. There is another group of values which are as bad on the other side. So plus 1.82 and z-values which are larger. If we end up in one of these red regions, we have something that is as bad as minus 1.82 or worse. So what we're dealing with is a two-tailed test. We're dealing with both tails of the bell shape. The next step is to compute the probability to end up in these red regions. That's something we can do with OpenOffice. So now I'm interested in the probability. Let's say probability times 100, so that I get percent. That's easier to read. So this is 100 times, and now the normal distribution at this z-value, mean 0, standard deviation 1, and I do not want to get the bell shape as such, I want to get its integral. This is why I enter 1 here, the accumulated version. Now it says 3.4%. So what we learn from that is that this area amounts to roughly 3%. And of course, by way of symmetry, this too amounts to roughly 3%. of the total area under the bell shape. So the probability that we're looking at, the probability of the z-value being in the red region that poor, is 3% plus 3%, 6%. Thus it's larger than 5%. 5% is the typical threshold for statistical significance. It's above that threshold, so we say it's not significant. It's something that we could expect. Its probability is above 5%. It's not a rare case. It's something that could very well happen if the hypothesis is true. Because it's not significant, we can't use this to reject the hypothesis. So no luck here. This hypothesis 1, that after treatment the blood level stays as it was, this hypothesis cannot be rejected on the basis of these data. Let's try a second hypothesis. Maybe we have more luck here. And this hypothesis says the expected value, mu, is larger than or equal to 6.00. So the equal sign has changed to a larger than or equal. The approach is the same. Let's compute the probability of z being minus 1.82 or worse. But the meaning of worse has changed in a subtle manner, because the distribution now is different. Actually, we do not completely know what the distribution is. If the expected value was 6.0, then z would be distributed like this, the regular bell shape centered at z equals 0. But if mu was 7, this would be the distribution of z. It would be shifted by 1 to the right. If the expected value was 8, this would be the distribution. And if the expected value was 9, we would end up here. And of course, the expected value could be 100, 1000, 24. It could be 2.712 or whatever. So we do not know which of these curves, which of these distributions is the right one. We only know it's one of these. That's the hypothesis. And now we have to think about what this means. Z is minus 1.82 or worse. On the left-hand side, that's pretty much what happened before. If, a big if, the expected value is 6. If the expected value is 6, this curve is valid, this distribution is valid, and hence we end up with a z-value of minus 1.82 or less in 3% of the cases. But if the expected value is not 6 but 7, you see, there is not much left of that curve. The resulting probability of having a z-value of minus 1.82 or worse would be smaller, even more so for an expected value of 8 or 9. So what we can say is that this area is 3% at most. We do not have a specific value, we can just say this area is 3% at most. That's one difference to the case before, and there is yet another difference to the case before. If we end up here at plus 1.82 or something, we cannot say anything about that. This would be perfect, for instance, if the expected value is 8, and we do not know if the expected value is 8. So, we simply have to ignore that one. We have to regard this as okay. If there are z-values above 0, then so be it. We can't do anything about them. This sort of test is called one-tailed, because we're just looking at one of these two tails of the bell-shaped curve. And now comes the important part. What's the probability of ending up with that z-value, or a worse one, well, that's 3%, which is smaller than 5%, the regular threshold for significance. So this is significant. Something has happened that is highly improbable. Its probability is below 5%. That's a significant event. And hence, we reject that hypothesis. That hypothesis led us to saying that what actually has happened is highly improbable. So we reject that hypothesis. What we learn is that this drug does not seem to increase that specific blood level.